Welcome to The Explainer. Today, we are tackling a massive challenge that literally trips up thousands of students every single year. Whether you are studying syllabus 0417, 0478, 0983, 0984, 2210, or what we're going to heavily focus on today, the Cambridge AS and A-Level Computer Science syllabus 9618, the problem is exactly the same. We're going to dive deep into section 10.2, arrays, but we're doing it through a lens I like to call the photographer. Why? Because getting top marks in a Cambridge computer science exam isn't just about dumping raw facts onto a page. It's about finding the absolute perfect angle. It is about framing your answer to highlight the exact key evidence the examiners are actively hunting for. Look, think about it like this. When I grade past paper responses, let's take a classic 9713 or 9618 past paper question, I consistently see two distinct types of students. Let's call our first student Alex. Now, Alex works hard, but Alex overloads their answers with raw computer science facts. They see the word array, and they write massive paragraphs of code. They list every single piece of theory they can remember, but there is zero analytical depth. It's a data dump. Then we have Sam. Sam is fighting the clock. Sam rushes through the exam, completely missing the specific command word requirements. The question asks them to evaluate, but Sam just describes what an array is. Sam gives a generic, rushed answer that doesn't actually solve the problem presented in the context. Both of these students, Alex and Sam, are losing massive points. And the tragic part? It's not because they don't know the material, it's because they simply do not know how to frame it. Today, we're going to fix that. We are going to transform your approach so you can secure every single mark available. Okay, let's dive into this.
Right off the bat, there is a stark, very real warning directly from the principal examiner reports. They state, most students lose easy marks on 10.2 arrays, technical terms, index, upper bound, lower bound. But after this, you won't be one of them. So why does this happen year after year? It happens because students fundamentally misunderstand how marks are actually awarded. In Cambridge computer science, it's not always about the final destination. It's not just about writing the perfect, bug-free final line of code. It is heavily about the journey. This brings us to a crucial concept, the method mark strategy. Examiners are actively looking to award you points for your process. If you establish the array bounds correctly, if you define the index accurately, and if you demonstrate logical systematic processing, even if your final algorithm has a slight bug at the very end, you can still scoop up the majority of the marks. Let me repeat that because it's absolutely crucial. The process earns points. That is your safety net. Mastering these technical terms is the very first step in building that net, so you don't end up like Sam, rushing and leaving all those method marks on the table.
So we have to ask ourselves, why do students find applying concepts to unfamiliar contexts so incredibly hard? You've studied the textbook, right? You know what an array is, you know what an index is, but then you sit in that quiet exam hall. The paper is flipped over, and they present you with a completely bizarre scenario. Maybe it's a factory automation system, or a temperature tracking matrix for a satellite, or a complex database for a veterinary clinic, and suddenly, your mind just goes totally blank. The reason this happens is because the assessment framework for 9618 demands connected, conceptual understanding. Rote memorization is a massive trap. If you just memorize the sentence an array is a data structure, well, that's not going to help you when the examiner asks you to evaluate the space complexity of a multidimensional array in a highly memory-constrained embedded system. You need a connected understanding. You have to know the why and the how, not just the what. You need to be able to abstract the core principles of arrays and drop them into absolutely any context the Cambridge examiners throw your way. That's the difference between a passing grade and a top-tier score.
To get you to that level of absolute mastery, we've structured this explainer into a definitive blueprint. We're going to decode the mark scheme matrix, lock in those array foundations so they're bulletproof, build a procedural framework, analyze those critical examiner warnings so you don't repeat the mistakes of past students, and we'll finish with a final strategy blueprint. But really quickly, before we continue and unlock the secrets of the mark scheme, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's move to the first section and see exactly how this builds your mark potential from a flat 0 to 100%.
Section 1. Before you can win the game, you absolutely have to understand the rules. The academic benchmarks for the Cambridge computer science exams are strict. They require highly logical and completely structured reasoning. When you see command words in your exam, words like evaluate, compare, explain, or describe, listen to me carefully. These aren't just polite suggestions from the examiner. They are strict directives that map directly to assessment objectives. If a question asks you to evaluate an array structure and you merely describe it, like our friend Sam often does when rushing, you will cap your marks instantly. It literally doesn't matter how accurate your description is. If you don't evaluate, you lose.
So how do we fix this? We use the Peel framework. Point, evidence, explanation, link. This is how top students structure their computer science answers. You make your point about the array, you provide the evidence from the specific scenario given, you explain the technical computer science reasoning, and you link it directly back to the command word's objective. This framework forces you to construct an answer that the examiner has literally no choice but to award full marks to.
Let's look at this comparison, because it brilliantly illustrates the exact difference between our two students from earlier, Alex and Sam, and what a top-tier candidate actually looks like. Superficial breadth is Alex. It's writing down everything you know about arrays. Alex might mention they hold data, mention they have an index, maybe draw a little box on the paper, but Alex never analyzes how they solve the specific problem. It's all point and no evidence, explanation, or link. Analytical depth, which is what the Peel framework prioritizes, is entirely different. It's identifying the specific data structure required, justifying exactly why an array is optimal for time complexity in this given context, and proving how the index allows direct access to memory locations. By focusing on analytical depth through the Peel structure, you move from just stating random facts to actually proving your computational competence to the examiner.
Moving into Section 2, the theoretical architecture. Let's be totally honest here. Precise definitions are the absolute bedrock of high-scoring exam responses. You simply cannot achieve analytical depth if your foundational terminology is shaky. Examiners tell us year after year that candidates who reference cross-topic connections achieve significantly higher marks. For example, if you can link the abstract concept of an array index to how physical memory addresses are accessed at the actual hardware level, you blow the examiner away. It shows you aren't just looking at programming in a vacuum, it proves you understand the entire computer system. So we're going to lock down the 3 most critical technical terms right now. We're going to define them exactly how Cambridge wants to see them, and we're going to look at how to frame them using our strategy.
First up is the index. The precision of this definition is key. The index is the technical term used to pinpoint the exact position of a data element within an array. Don't just call it a number or a spot or a location. Those are weak terms. It is a logical identifier that maps directly to a physical memory offset. When top candidates write about an index using the Peel framework, their explanation, the E, actively references how the system calculates the memory address. They understand that if the base address of the array is known, the index is literally the multiplier used to jump to the exact piece of data in O1 time complexity. When you write your answer, use the specific term index to show you understand systematic data retrieval. If Sam rushes and just says the array looks for the data, Sam gets a red mark. If you say the algorithm utilizes the array index to directly access the element in O1 time, you get a massive green check mark. That is the perfect angle.
Moving to the next crucial term, the upper bound. The upper bound is defined as the maximum valid index limit in an array structure. Why is this so important to Cambridge examiners? Because in real-world computer science, crossing the upper bound isn't just a minor oops mistake on a test, it is a critical system failure. It leads to buffer overflows, catastrophic memory corruption, and massive security vulnerabilities. When the exam asks you about algorithmic testing or tracing code, they are desperate to see you explicitly checking the upper bound. Here is a massive memory hack to help you lock this in for exam day. Create a mnemonic using the first letters of these key terms: index, upper bound, lower bound. Think of it as I understand limits, index, upper, lower. Whenever you sit down and see a 9618 question about arrays, immediately write I understand limits in the margin of your paper. It will physically force you to ensure your answer has addressed the index, checked the upper bound, and verified the lower bound.
And naturally, that brings us to the lower bound, the minimum valid index starting point in an array. This seems incredibly simple, right? Usually it's 0 or 1, depending on the specific language paradigm or pseudocode standard Cambridge is using for that particular question. But you would be shocked, literally shocked, at how many students lose marks by writing a rushed loop that tries to access an index below the lower bound. Integrating these precise definitions, index, upper bound, lower bound, seamlessly into your Peel paragraphs demonstrates absolute mastery. It shows you are thinking like a real software engineer, anticipating edge cases before they break your system. Stop scrolling for a second and look at me. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 whole grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to the framework.
Now that we have the exact vocabulary locked in, we have to shift our focus to applying them through algorithmic thinking. This is where the magic really happens. Algorithmic thinking requires step-by-step decomposition. You have to select the appropriate data structure, implement the code efficiently, and test it rigorously. You can't just jump straight into writing code on the exam paper the second you read the prompt. That is exactly what our rush student Sam does, and it leads to total disaster. You need a standardized sequence. You need a framework that protects you from your own exam anxiety and ensures you extract every possible mark from the data interpretation requirements. Let's look at what that actually entails.
Okay, let's step into an interactive workshop. Imagine I'm putting 60 seconds on a visual timer right now. We are going to do a rapid data scan using this 5-step standardized sequence. This is your ultimate blueprint. Step 1. Deconstruct the question. Identify the exact command word. Are they asking you to trace an array, evaluate one, or declare one? Step 2. Extract relevant data. Scan the complex computer science chart or graph they gave you. What is the context? What are the specific bounds? Step 3. Select the analytical framework. How are we navigating this array? Is it a linear search, a bubble sort? Step 4. Execute with clear notation. This means using the exact pseudocode standards required by your specific syllabus. Step 5. Present with correct terminology. Bring back your index, upper bound, and lower bound. This 5-step sequence is exactly how you systematically extract data, perform calculations, and draw evidence-based conclusions, without getting lost in the weeds like Alex does.
We are now making a critical pivot in this explainer. Let's do an autopsy of failed answers, based directly on insights from principal examiner reports. These are the people grading your papers, and they are practically begging students to stop making these specific, repeated errors. When a complex computer science chart or data table is put in front of a student, panic sets in. Instead of using that 5-step procedural framework we just covered, they revert to bad habits. Let's look at exactly where students hemorrhage the most marks when dealing with arrays and algorithmic data structures, so you can avoid these traps completely.
Let's play a little game of Find the Flaw. I'm going to show you 3 common pitfalls. I want you to imagine a 60-second timer on the screen and think about how these ruin an answer. First flaw. Forgetting to check overflow and edge cases. If you write a loop to populate an array, but you don't explicitly tell the program to stop at the upper bound, your code overflows. Boom, method marks lost. Second flaw, ignoring boundary conditions. This ties directly into the first point. The boundaries, the upper and lower bounds, are your literal guardrails. If you evaluate an algorithm and fail to mention how it handles the absolute limits of the data structure, your analysis is incomplete. Third flaw, providing answers not specific to the given context. This is huge. If the question is about an array storing temperature data for a greenhouse, and your paragraph talks generically about storing integers, you lose the context mark entirely. Failing to check edge cases or leaving answers disconnected from the specific context guarantees a loss of easy marks. If I gave you 30 seconds right now to write a perfect peel paragraph, your link must connect back to the greenhouse, not just general theory.
For our final strategy blueprint, we are focusing heavily on critical analysis and evaluation. We are moving way past simply writing a basic loop or declaring an array. We are now looking at higher-order assessment objectives. The A-level standard demands that you evaluate alternatives. Why use a 1D array instead of a 2D array? Why is this specific search algorithm more efficient on this specific dataset? You have to formulate justified recommendations. This requires taking all the foundational knowledge, the indices, the bounds, the context, and synthesizing it into a compelling, analytical argument using the Peel method.
When you are asked to evaluate algorithm quality regarding an array, you must systematically address these 4 pillars. This is your time management matrix. Time complexity. How fast does your loop run from the lower bound to the upper bound? Is it O of n? Space complexity. How much memory is this array taking up in the system? Edge cases. What happens when the array is entirely empty or completely full? Effect on performance. How do these factors impact the overall system in the context of the prompt? By breaking problems into these logical steps and checking for reasonableness across these 4 pillars, you build an ironclad answer. You aren't just guessing, you are systematically proving your evaluation. Students who implement these computer science strategies see an average improvement of 2 whole grade boundaries, but only if they practice consistently with our weekly explainer videos.
And this brings us to our ultimate exam hack. Show you're working. Method marks can save you even if your final answer is wrong. Let's say you mess up the final line of code under exam pressure, but you clearly defined the upper bound, you correctly referenced the index, and you showed systematic processing.
The examiner will award you marks for every correct step you took. Showing systematic processing and clear working is your ultimate safety net. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by without mastering these strategies.
I want to leave you with this final provocative thought. Which part of the deconstruct, solve, evaluate framework will you apply to your next past paper? Are you going to finally focus on nailing those precise boundary definitions so you don't lose method marks like Sam? Are you going to ensure your time complexity evaluations are actually context-specific instead of just a data dump like Alex? I challenge you to immediately apply this array methodology to your revision right now. Never let another easy mark slip away because of poor framing. Drop a comment below with your target grade for computer science and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.